Magnetic field, the region around a magnet in which magnetic force applies on another magnet is called magnetic field. Like poles of a magnet repel each other, while unlike poles of the magnet attract each other. North pole repel North pole, South pole repel South pole of other magnet. A bar magnet is shown in the figure having North pole and South pole. If iron filings are placed nearby it, then the number of pieces at poles are more in number because there is a stronger magnetic field, whereas number of pieces are smaller in the middle due to weak magnetic field of bar magnet present in the middle of bar magnet. Lines of magnetic field are shown in the last figure at the bottom. They are starting from North Pole, eliminating at the South Pole. Lines of magnetic field are more in number at the North Pole. Therefore, iron filings collect more in number at the poles, North Pole as well as South Pole. Lines of magnetic field are the closed curve starting from North Pole of the magnet and eliminate at South Pole of the magnet. Like poles repel and unlike poles attract each other. Two magnets are shown. North pole of the magnet is toward South pole of the magnet. Then lines of magnetic field starting from North pole of the magnet goes to South pole of the magnet of other magnet, and there is a force of attraction between North pole and South pole. Whereas in the other diagram, North pole and North pole are kept in the two magnets closer to each other. Lines of magnetic field change their path and they are not going from North pole to North pole, but they are moving away from other North pole of the magnet present there, as a result of which there is force of repulsion. These lines of magnetic field are showing force of attraction in between the opposite poles, North and South pole in diagram 1, and force of repulsion in another diagram 2. Here is a compass needle. Compass needle, basically it is a magnet in which North pole and South pole, North pole is red shown here and white is South pole. When it is placed in a horizontal plane, it always takes north and south direction due to presence of Earth magnetic field. Earth magnetic field direction is from south to North pole, that is Earth magnet North pole is placed in the south direction and South pole is placed in the north direction. Like poles repel each other, unlike poles attract each other. Therefore, there is force of attraction and repulsion between Earth's magnetic field and magnet shown in compass needle, as a result of which the compass needle shows deflection in north and south only. Here is a magnetic needle used for magnetic field in a vertical plane. In the previous diagram, compass needle is used for magnetic field in horizontal plane only, and here is magnetic needle used to measure magnetic field strength in a vertical plane only. Activity of lines of magnetic field. A bar magnet is placed on cardboard on which a plain A4 size paper is placed and boundaries with the pencil are drawn around the magnet so that on shifting magnet we can replace the magnet at its original position. Now near the North Pole, compass needle is kept. North Pole attracts the white portion of compass needle. South Pole, as a result of which North Pole of compass needle goes away, and with the help of pencil, put a dot near the just close to the North Pole of the compass needle. Then South Pole of compass needle is kept on the dot and another North Pole position is again pointed out or dot is placed on the North Pole. Again the South Pole of compass needle is kept on the dot and new dot is placed on the North Pole. That is, always we are placing North Pole a pencil dot so that new position is going on, as a result of which various positions of compass needle are located with the help of dots. Join these dots and closed curve are formed around a magnet having north and south pole as shown in figure 1. Magnetic field lines. Magnetic field line is a curve around a magnet such that the tangent at any point on the curve give the direction of magnetic field at that point. If magnetic field lines are very close to each other in a particular region, then the magnetic field is a strong magnetic field. If lines of magnetic field in a region are far away or small in number, then the magnetic field is a weak magnetic field. Properties of magnetic field lines. Number 1, magnetic field lines are closed continuous loops or curves. Number 2, two magnetic field lines can never intersect each other. Number 3, the tangent at any point on a magnetic field line gives the direction of magnetic field at that point. 4th, the magnetic field lines are crowded in a region of a strong magnetic field far away from each other in a weak magnetic field. That is the differentiation. That is, we are differentiating between weak and strong magnetic field. Lines of magnetic field are parallel to each other in a uniform magnetic field. If the lines of magnetic field are not parallel, the magnetic field is known as non-uniform magnetic field. Earth magnetic field. The Earth behaves like a magnet due to its spinning about its axis. The direction of Earth's magnetic field is from south to the geographical north as shown in figure. Here is Oersted experiment, and this Oersted experiment shows here current is flowing in a wire placed above a compass needle. When the current is flowing in the conductor, then compass needle shows deflection. If the position of compass needle is different, say below conductor, above conductor, one left hand side of conductor, right hand side of conductor, then direction of compass needle is also different. And in the last diagram, direction of field is shown in a circular shape, and concentric circles are formed due to presence of magnetic field of the current carrying conductor around it. Oersted experiment. Oersted observed that when an electric current is passed through a conducting wire, a magnetic field is produced around the current carrying wire. The presence of magnetic field at a point around the wire can be detected with the help of a compass needle. Factors on which magnitude of magnetic field depends. Number 1. Strength of magnetic field is directly proportional to the current passing through the conductor, that is B, magnetic field strength, directly proportional to the current I. Second, the strength of magnetic field is inversely proportional to the distance r of a point from the conductor. The distance increases, magnetic field becomes weaker. Right hand thumb rule. If we hold the current carrying conductor in right hand such that thumb points in the direction of flow of current, then finger encircle the wire in the direction of magnetic field. Here again, right hand thumb rule. Current is flowing in the conductor and thumb is placed in the direction of flowing of current and fingers are wrapped around current carrying conductor. When the current is flowing, magnetic field is produced by current carrying conductor around it, as a result of which the fingers are showing here direction of magnetic field in the form of circles. These are the concentric circles. On increasing distance from current carrying conductor, the strength of magnetic field decreases. There is activity for drawing lines of magnetic field on a paper. A cardboard is set in the diagram on which A4 size paper is placed and compass needle is placed around a current carrying conductor. On increasing resistance, the current decreases. On decreasing resistance, current increases. Therefore, various concentric circles are drawn with the help of compass needle. On changing the value of current, and this is done with the help of a rheostat, that is a variable resistance. Flux is concentrated where flow directions coincide. We are observing here a current carrying conductor and another current carrying conductor shape that is joined combinedly. We can say a wire is in the form of a loop. Then one side is producing anti-clockwise magnetic field, right side is producing clockwise magnetic field. In this way, the both magnetic field are present due to left hand side portion of the wire as well as right hand side of the portion of the wire, and a circular loop is also can be explained on the basis of it. It is producing a magnetic field and lines of magnetic field starts from north pole, eliminate at the south pole. Therefore, this loop or this a curve having a current producing north pole in front of the paper and south pole in the back side of the paper. Here is the activity of a circular loop to show presence of magnetic field, that is north pole and south pole of this magnetic loop. One side in front of the loop we are having north pole and opposite direction south pole, because lines of magnetic field always start from north pole, eliminate at the south pole. This activity, just like a bar magnet, place compass needle around the left hand side, say A portion, and then put the dot on north pole of the compass needle, place south pole on the dot, and again put a dot on the north pole. In this way, successively we are placing dots and draw concentric circles. Solenoid. When wire coils are formed into a series of continuous loops called a solenoid, the effect described above produce a magnetic field pattern that is similar to that around a bar magnet. A solenoid is a long helical wound shape of insulated copper wire. It can behave like a electromagnet if soft iron core is placed inside it. It is an electrical device to produce permanent magnet. If we want to produce permanent magnet, then a steel piece is placed inside a solenoid and strength of magnetic field increases successively so that north pole and south pole are generated. On increasing current more and more, the strength of magnetic field increases, and this is a slow process to produce a bar magnet, but bar magnets are produced after keeping a iron or steel piece inside it. That is, temporary magnets are produced with this technique. Strength of magnetic field can be increased by number 1, increasing current, and number 2, increasing number of turns of the coil per unit length. On increasing number of turns, length of the current carrying wire increases, as a result of which stronger magnetic field is produced according to Oersted experiment. Similarity between the magnetic field of bar magnet as well as solenoid. Lines of magnetic field are producing from north pole of magnet and eliminate at south pole. Similarly, in the case of solenoid, these are just like it. All the characteristics are similar to the bar magnet magnetic field lines, and if the direction is clockwise, current direction is clockwise, then it is a south pole in the solenoid. Direction of current is anti-clockwise, it is a north pole in the solenoid. That is also known as clock rule also. Clock rules is applied in solenoid to find the magnetic poles produced, that is north pole and south pole produced by the current carrying solenoid. Electromagnet. When a soft iron bar is placed, this soft iron bar is known as core, C-O-R-E, placed inside a current carrying coil or current carrying solenoid, it behaves like a magnet. As long as current flows through the coil, such a magnet is called electromagnet. Electromagnets are used in electric bell, they are used in industries to lift heavy iron pieces or iron scrap to avoid the working of lever, so that the transportation of iron scrap collected from cities is an easier task after using electromagnet. Difference between permanent magnet and electromagnet. A permanent magnet, it cannot be demagnetized easily. Electromagnet demagnetize when electric current becomes zero. Therefore, electromagnet is a temporary magnet. Number 2, the polarities north and south poles of permanent magnet cannot be reversed. They are fixed. Electromagnet, the polarities of an electromagnet can be reversed, interchanged on reversing the direction of current. Permanent magnet, a permanent magnet produces weak magnetic field. Electromagnet produce a strong magnetic field. Here is a MRI machine in which the patient is kept inside the MRI machine, and here magnetic images are developed with the help of outside magnetic field, and diagnosis of the body is done on the basis of it. Magnetism in human body. Blood contains sodium and potassium ions which cause weak electric current as the blood circulates inside the body. These current produce weak magnetic field in our body. The magnetism in human body is used for generating functional images of different parts of the body. This technique is called magnetic resonance imaging, MRI. Force on a current carrying conductor placed in a magnetic field. Magnitude of the force experienced by current carrying conductor placed in a magnetic field depends on the following factors. Number 1, directly proportional to current. More current is produced, it is producing a stronger magnetic field, and then force is also increasing. Basically, this is application in electric motor. In a DC electric motor, current is more, then force applied is more, and speed of rotation of the motor becomes more. Second, directly proportional to external magnetic field. In a DC motor, there is magnetic field, but nowadays the magnetic field is generated with the help of coils, and this magnetic field is stronger, then speed of the motor becomes more due to stronger magnetic field, force becomes stronger. And point number 3, force is directly proportional to length of the conductor. A heavy motor, say 5 kilowatt, 10 kilowatt, 25 kilowatt or more, number of turns becomes more in the coil, that is, length of the coil becomes more, as a result of which the strength of the motor becomes more also. Fourth point, force is directly proportional to sin theta, where theta is the angle between direction of magnetic field and direction of current flowing in the conductor. Force F is equal to ILB sin theta. Force on a current carrying conductor placed in a magnetic field. Here is a U-shape or horseshoe shaped magnet having north and south pole. Magnetic field is produced from north pole, and lines of magnetic field starting from north pole are eliminating at south pole. In between the poles of magnet, a current carrying conductor AB is placed. When the current is flowing inside it, the current carrying conductor produces a magnetic field around it according to the Oersted experiment. This magnetic field and another U-shaped magnetic field, two magnetic fields are present there. There is force of attraction or repulsion between unlike poles, and like force, as a result of which there is a deflection in the current carrying conductor AB, and this is the activity just like the working of DC motor. Fleming's left-hand rule. In left-hand rule, if we stretch forefinger, middle finger, thumb mutually perpendicular to each other, forefinger shows direction of magnetic field, middle finger shows direction of current, then thumb will give direction of force acting on current carrying conductor placed in magnetic field. Statement: if we stretch our left hand in such a way that forefinger, middle finger, thumb are mutually perpendicular to each other, forefinger shows direction of magnetic field, middle finger shows direction of current in a conductor, then thumb will give direction of force acting on current carrying conductor placed in magnetic field. Here is the basic of electric motor is shown. Two magnets, North Pole and South Pole. They are producing here magnetic field between the region, and a current carrying conductor is placed. When the current is flowing, force is acting in upward and downward direction according to Fleming's left-hand rule discussed, as a result of which a torque is generated on the armature coil. This loop basically is known as armature, and this armature rotates in the rotational motion. These two forces are replaced by the word torque, and this torque rotates the armature coil in magnetic field when current is flowing through it. Here are the electromagnets shown in figure. In the industries, electromagnets are working in place of human labor, and they are very strong. They are lifting iron scrap. Iron car is also shown. Here a crane is lifting iron car with the help of electromagnet. Thank you.